Okay. Today we'll continue with the same chapter, elasticity. Last class I talked about stress. I talked about strain. Stress upon strain is equal to E. E is called modulus of elasticity. And this relation holds true only within the elastic limit. I gave one example yesterday, which is more elastic, rubber or steel? What is the answer?
Steel.
You know the reason? Because for the same strain, stress is more in elastic.
So you are not audible. Sir is talking to someone.
Hello. Okay. Can you hear me?
Yes, sir.
There was a phone call. When phone call comes, no, then you will not be able to hear me. Yeah? You will not be able to hear you. Okay.
Okay, sir.
Ready, yeah?
Yes,
So,
sir.
steel is more elastic than the rubber. Okay. Yesterday only I told you there are three types of E, which modulus of elasticity. Right on. Types of modulus of elasticity. Types of modulus of elasticity. Types of modulus of elasticity. Denoted by E, capital. There are three types, right? Number one. First one is Young's modulus. Young's modulus. Young's modulus of elasticity denoted by Y. Okay. Any kind of modulus will be ratio of stress to the strain. Stress by strain will be the value of E. And all are actually ratio of stress to the strain. We write like this, Y equal to, here we will be writing longitudinal stress to the longitudinal strain. Which one you like? Longitudinal stress to the longitudinal strain. Longitudinal is also known as lateral. Okay. Longitudinal is lengthwise. Longitudinal stress is when you are applying a stress, that means you are giving a pressure and you are changing its length. Such a modulus will be called Young's modulus. When we apply a pressure and we change the volume of the body, we are changing the volume of the body, then it will be second one, bulk's modulus, bulk. Bulk means actually volume, okay, bulk's modulus. And when we are applying a stress and the shape is only changing, so that will be called shear modulus, third category of modulus, third category, just keep in mind. Length, first one is length one, second is related to volume, and the third is related to the shape of the body, shape. Okay. So longitudinal stress formula we write here, force by area, but normal force. The force will act normal to produce change in the length. Here I will write directly F by A. Stress formula is F by A. But the force will be normal force. It is same as pressure. Longitudinal stress value will be like this: delta L by by capital L. Change in length per original. This change in length we can write as elongation. Elongation, length, increase in the length. Or expansion, you can call it expansion. That we can denote by either delta L or small e. The delta L or small e we can denote that by. Now, if you arrange it, it will become F by A, and here this will be turning upside down into delta L, capital L will come up. This is the value of Y. Y value is coming FL by A delta L. Okay. What can be the unit of Y? Unit we can write Newton per meter square, because this one strain doesn't have a unit. So Newton per meter square, or we can write even Pascal for it. What are the examples? The common example, we have a rubber band, we are applying a force and stretching it. We are increasing its length. So what modulus will be effective there? Okay, Young's modulus. Young's modulus. Spring is made up of steel. Suppose we are having a steel here like this. Steel is there. Spring is there, and we are keeping some weight over here, W. So the spring will get elongated, will get stretched. What modulus will come into play? This modulus, Y. This is the force, this value of force. This may be a weight, maybe 5 kg weight, 10 kg weight. Own weight also it will get expanded. If it is a quite heavy spring, when you do like this, so the spring gets elongated itself. So sometimes the weight of the body itself will cause elongation in it. Maybe a steel wire, we'll take a steel wire like this, steel wire, thin steel wire, and you are hanging some weight over there. The steel wire also will get stretched, but it may not be visible to us. When you measure with the help of instruments such as measuring tape or a ruler and all, you will find there is increase in its length. Slight increase may be there, maybe by 1 millimeter or by 0.5 millimeter, but that there will be some increase. It may not look visible, but in case of rubber cord and all, it was, once you suspend some weight, it gets elongated too much. So, when the strain is more, then Y will be less. When the strain is less, Y will be more. But this is the formula of Young's modulus. Hope you understood it. Tell me anything you want to clarify, you can. It's okay. What is your idea?
Okay. Sir,
Okay, thank you. All right. Now I'm coming to the second category now, number 2. Right here, bulk's modulus, elasticity, and this is denoted by K. Bulk modulus is denoted by K. Okay. K. K is equal to, here we'll be writing volume. This will cause change in the volume, right? A volume stress to the volume strain. Volume strain, or with that bulk stress to the bulk strain. Bulk means, volume. Bulky, which in the bulk of liquid, this person is very bulky. That means it's occupying more space. The man has greater volume. That is the meaning. So K is equal to volume stress to the volume strain. And the formula will change. Volume stress formula will be the same, it is same as pressure. And here we will be writing change in volume by original volume, like this. Change in volume by original volume, not length, but change in the volume. volume, delta V by V. We write that. And finally, your equation becomes F by A, delta V, and V will come up. So this will be K, and unit will be the same, Newton per meter square or Pascal. Okay, finished? Okay, finished.
Yes, sir. Yes, sir.
Okay. Same way, actually, y is lengthwise, this is volume, but just keep in mind, otherwise the formula is same. But now here, just one thing to be noted. Solid only has got length, so elongation will take place or expansion in the length will take place only in case of solid. Liquid doesn't have a length. Gas also doesn't have a length. K is applicable for all three states of matter like solid, liquid and gases. But Y is only applicable for solid. So this is a general formula we write. This is for a solid, but for a gas, particularly for a the same formula can be, modified for a gas like this. K equal to, we write, force by area. What does it make? F by A will make what? Pressure. We can write like this. PV by delta V. But for a gas, the same formula is written with a minus sign. This is for gas. Minus sign signifies Boyle's law. You can write below that. Here minus sign signifies Boyle's law. What is Boyle's law? Pressure is inversely proportional to the volume. That means with the increase of pressure, volume of the gas decreases. Then delta value will come negative. When we apply the pressure, the delta V in the volume will come negative. For example, initial volume was 100 units, 100 centimeter cube, 100 units, and the new volume will be anything but less because when we increase the pressure, volume decreases. So suppose new volume is 90. What is the value of delta V? The delta V value will come final minus initial. Final is 90 and initial is 100. So 90 minus 100 will come negative. So this is negative, that's why, and K should always be a positive quantity. So negative cancel and K will come positive. K cannot be a negative quantity because K is all ratio, no? So ratio should not be negative. So here negative sign indicates Boyle's law, which means with the increase of pressure, the volume of a gas decreases. So that is the idea. This formula, gas will be written with a minus sign. And for liquid and for solid, no minus, you may not give minus sign, you can directly write PV by delta V or P means F by A, or you can write like this. Hope you have understood. Tell me any queries, any questions in your mind. Nullify. Yes?
Clear.
Clear. Okay, thank you. More formula, write down here compressibility is equal to 1 by K. Compressibility is reciprocal of Bulk's modulus. Just get this formula. Compressibility. How compressible a substance is, or a gas is, or a liquid is. How compressible. The value of K is less for gas. So compressibility will be more. That means gases are more compressible than any other. Gas you can compress more because there are large intermolecular space. No? Molecules are far apart, so they are more compressible. You can compress them by a greater margin. you can decrease the value of delta V by a greater value. So for a gas, K value is more. So K value is less, so compressibility will be more. Okay, just keep in mind. Yeah, any question? Any question?
No, sir.
Okay. Now the next one, third one is shear modulus. Just at shear modulus or modulus of rigidity, or write down another name also, modulus of rigidity. Modulus of rigidity. Denoted by N. Shear modulus or modulus of rigidity. So I write that N. Small n. What is modulus of rigidity? Write down. It is the ratio of shearing stress, shearing strain. Shearing stress to the shearing strain. What is shearing stress? This time the force applied will be tangentially, okay, tangent-wise, not normally, not perpendicularly. We are only changing the shape. This is related to the changing the shape, not changing dimension, but changing the shape only. Slight change in the shape. So, I can give one example here. We are having a body here, and I'll give a force. This way I'm giving a force, like this way. Slanting I'm giving. So you see there is change in the shape of the body. The modulus of elasticity related to the change in the shape is known as this one, shear modulus. And this is measured by shearing stress to the shearing stress. Shearing stress is tangential force, but not the normal force. Tangential. Formula will be same only, F by A. And the change in the shape, that is change in the angle only. Slight change in the angle is denoted by theta. Here I write here F by A theta. And the unit of this we write will be Newton per meter square. This time we cannot write Pascal. Why we cannot write Pascal? Because Pascal is pressure, and pressure is the normal force acting per unit area, because that time the force must be normal. But shearing stress time the force is not normal. Force is tangential, tangent-wise. And the unit is Newton per meter square. That means Newton per meter square is a general unit or universal unit for all the three, YKL. Whereas Pascal we can use only for Y and only for K, not for this. Okay, but your main focus should be on the first two categories of modulus, not on the second category. The main first one is the most important type. This is just to have a knowledge only about it. So this type of modulus we have done. Now, next heading you give. Next heading is Poisson's ratio. Poisson's ratio denoted by the symbol like this, sigma. Poisson's ratio related to elasticity. Okay. It is a ratio, but ratio of what? Let us know. Sigma is equal to, it is a ratio of lateral stress, lateral strain to the longitudinal strain. So we will be writing like this, lateral ratio of lateral is longitudinal, lateral strain to the longitudinal strain. I'll tell you what is it actually. I'll tell you. Give example also. Okay. We are having a wire. Maybe steel wire, maybe rubber wire. We are elongating it. When we are elongating it, so increasing the length, you will find the length changes as well as the diameter also changes. When the length increases, what happens to the diameter?
Decreases.
Decreases, yes. Or when the length will decrease, the diameter, it will become, more inflated there, that means the diameter will increase. Reverse will happen. So, we are finding change in both length as well as diameter. Diameter is side-wise change also will take place, that is called lateral. And longitudinal is related to only length. So, change in diameter per original diameter is called lateral strain. And change in longitudinal is lengthwise. Long means length. Change in length per original longitudinal strain. So, let us write down lateral strain. Formula will become delta D by capital D. Change in diameter per original diameter, and longitudinal strain will be change in length per original length. Yeah. It tells you with respect to the longitudinal strain or with respect to the increase in the length, how much change will take place in the diameter. In some materials, the diameter will change more, in some materials, change will be less. But when we elongate a body, so diameter also changes. But in some cases, the change in diameter will be negligible. So they will have very low value of Poisson's ratio. This part will be very small, so it can be negligible. So sigma value will be very small, maybe nearly zero. You can say that hardly any change in diameter. But zero is not possible. Okay, zero is not possible. And we put a minus sign here. This formula also we put a minus sign here. Can you tell me why minus sign is used? Why is the sign of this equation is minus? Can you guess?
With the increase in length, dimension decreases.
Diameter decreases. Very good. That is the idea. With the increase in the length, the diameter decreases, and sigma is the ratio. No, it has to be a positive quantity. How can we have answer positive? This thing has to be negative because negative will become positive. So minus sign indicates or signifies that the increase in the length causes decrease in the diameter. For that reason, we are giving a minus sign. Have you understood?
So you were telling how it becomes minus cancelling each other.
When you increase that, no, when delta L is positive, then delta D will be what? Negative, no?
Yes, sir.
Increase in the length will cause decrease in the diameter, so delta D will shoot some negative. So the diameter is decreasing from original value. So this portion value will, when this is positive, and this will come negative. So negative becomes what? Positive. Sigma is our ratio, the positive ratio. Similarly, when the length is decreasing, just take the opposite. Length is decreasing, that is minus, and the change in the length is negative, then this will be a positive. Anyway, this minus will cancel, and answer will come positive. So minus sign signifies that increase in the length, decrease in the diameter, and the vice versa. So because of that, we assign a negative sign in the equation. Okay, the value of sigma lies always this much. Value of sigma, value range of Poisson's ratio. Range of Poisson's ratio always lies between 0. Actually, 0, there is no equal sign. Include between 0 and 0.5. Between. When the diameter becomes half of its original diameter, no, what happens beyond that, wire will break. Wire will break. So the value of sigma lies between 0 and 0.5. Such a ratio is called Poisson's ratio. Hope you have understood. Have you? Have you understood? Okay.
Sir, what is that sign name? Name of that sign?
Sigma. S-I-G-M-A. Sigma.
Okay,
This
sir.
symbol is also read as sigma. Okay. In mathematics, sigma means like this, so this is called sigma. But here in physics, this symbol is small sigma. Okay. It is a letter, Greek letter, sigma. Okay, now next heading you give in class 10, you used to learn that there are two types of potential energy. There are two types of potential energy. What are they? Can I ask you?
Gravitational and elastic potential.
Gravitational and elastic potential energy. Very good. There were two types of potential energy: gravitational and elastic potential energy. Yes. What is the formula of gravitational potential energy? Tell me. What is the formula
MgF.
of gravitational potential energy? mgh, yes. And with respect to the center of the earth, the formula was minus gm m by r, capital R, on the surface of the earth, and at other places small r. And we had done in the chapter gravitation. But now the potential energy related to elastic body is called elastic potential energy. Now we are going to derive a formula for that. Now you will be learning the formula of elastic potential energy. Okay. Write down, give the heading now, elastic potential energy, elastic potential energy, and we denote by U. Denoted by capital U. This is the heading. Elastic potential energy. Okay? Write down who suggested that, who is who, you know that, who was a scientist, who suggested that the force F, just as the force F, capital F, of deformation, the force F, capital F, of deformation is directly proportional to the elongation produced, directly proportional to the elongation produced in the body, within the elastic limit, F is directly proportional to the elongation. Elongation we can add delta L, or you can add small e. Small e means elongation. Directly you can write, or I'll add delta L. It's all the same. You can add even x, delta x also you can add. Just add x. X means elongation, change in the length. I think you all know, when we increase the force, elongation will be increasing, no? But of course, within a particular limit. We are having a string here. First case, I am suspending a weight of 1 kg weight. So elongation, you see something. 2 kg weight, more elongation. 3 kg weight, more elongation. 4 kg weight, more elongation. But don't put too much weight. If you put up 1000 kg weight, then this will not withstand, it will break. So there is always a limit. Within the elastic limit, F is directly proportional to delta L. Am I right or wrong? Tell me.
Yes.
Who suggested this? Who? Hooke's law he gave, no? That the same fellow. Who? He is not our da, okay? So now next line you write F equal to, this sign we change with equal sign by multiplying the right hand side by a constant K we write here, K delta L. You can write here where K is constant. Where K is constant. Okay? This constant K, if it is a spring, we call it a spring constant. If it is a rubber, we say rubber constant. If it is a kind of material given, so that material is constant. That will depend upon the ability of that material. And this K will have units and also have dimension. K will have units F by L, F by delta L, Newton per meter. And then accordingly you can find the dimension also. Yes.
So K changes with change in material.
K,
K's value changes with change in material.
K is constant. K value will be different, yes. In this, when you change force, delta F, then K is a constant for a particular material. Yes, your question is right. And you understood the answer. No, K will vary from one type of material to the other type of material. Within a spring also, different springs will have different values of K. Different spring will have different capacity. You know, some spring are made up of highly forged steel. I mean, very good quality, very strong kind of steel. Soft steel, or there are different types of categories of steel are there. Stainless steel we have, because nickel steel, alloys of steel. Some is called wrought iron, some is called cast iron. Various categories, it depends on that also. So F equal to K delta L. Okay, today we'll do this much. This topic is incomplete. From here only next class I will continue. Okay, not much left there in this chapter theoretically. Okay, theory part not much left. Maybe one more class we'll finish off this theory part, and then we'll be doing some problems. So today we'll do this much.
Thank you, sir.
Okay, thank you, boys.